So the synthesis problems that I put on the sheet are in no particular order. So if you are stuck at the first one, don't give up. They're of varying difficulties. Some of them are easier, some of them will take more steps. I'm going to do just a couple of problems, and I'm going to do them in the order of shortest synthesis steps to longest synthesis steps, and they range currently in the ones that I'm going to go over today from 2 steps to as much as 7 steps. You will not see a 7-step synthesis on the final exam, but if you do know how to do it, then you should be in really good shape. So the first one I'm going to start with is number 3, which might look challenging. I'm making observations here. We have an OH to a sulfur, so we change to SH3. There's no carbons being added other than the functional group change there, and then we also have a stereochemistry change. So we may want to do an SN2 reaction. So I'm going to start with the retrosynthesis, which is the backward synthesis. And if I want to do an SN2, I need to have something here with a leaving group. And if I look immediately back here, I already have the stereochemistry that I want to invert this one. And there's an OH here, which is a bad leaving group. So then I need to make it a better leaving group from the OH. So that's the backward synthesis. If I go forward now, we can make this a better leaving group by adding tosyl chloride, which converts it to an OTS. And now for the SN2, to get SCH3, for an SN2 I want to have a good nucleophile, which means it's going to be negatively charged, and the stereochemistry is already inverting here. So what I can just do is add NaSCH3, and then I get the product that I desire. So that is the first one. This one was only 2 steps long. So again, we have the OH, we made it into a better leaving group. The stereochemistry switched, we want to do an SN2 reaction, so you want to make sure you have the good leaving group and the good nucleophile to do that reaction. The next one I'm going to look at is number 8. In number 8, we have a bromine on the end, and we're trying to make an alkene in the middle. So we're going from bromine to alkene. Bromine was on the end, and the alkene is in the middle, so we're changing functional group position. And it might seem like it's kind of tricky because we have to move the bromine so many carbons in, but if you think about it, here we're doing our retrosynthesis. I can have a BR at this position and do that elimination, which isn't that far off from here. One of the tricky things about this one is the BR is on this end and the alkene looks like it's coming from this end, but if we flip the molecule over, it's the same thing. So I can get to there from here, and I can get to there from there. So this one is only going to be 3 steps. So if I start at the beginning, I just need any base, so I can use DBU. You can use DBN. You can use sodium hydride. T-butoxide also works here because the leaving group's on the end, so that would work as well. And that will give us this alkene here. We want to go to this bromo at the secondary position, or the Markovnikov, so then you would use HBr. And now we wanted to do this elimination. I don't want the terminal alkene, so I'll use a smaller base to get that product. And if we switch it around, this is named 2-pentene. This is also 2-pentene. So this one was only 3 steps long. Observations to make in number 12 here. We're adding carbons. 3 carbons. We need an anti-dibromo. Those are the 2 big things there. If I work backwards with this one, I know I can put in an anti-bromo if I have an alkene. Here's a triple bond here, so we're going to see a triple bond somewhere. One, two, three, four, five, six. 1, 2, 3, 4, 5, 6. And I can add carbons from this alkyne, which is the same as that one. So this goes all the way back here. So if I start my synthesis with propine, I start with NaNH2. We're adding 1, 2, 3 carbons, so it's 1, 2, 3, and a bromine. So I have my 3 carbons. I need to go to the E alkene, which requires sodium liquid ammonia. And that will give me the correct stereochemistry here. Br2 will get me the dibromo compound that is going to be anti. This is the 4-step synthesis here. This one is number 10 on the sheet. Observations, add 2 carbons. We have to add also an alkene. So I know that I need to add carbons here, so I probably have to go through some sort of alkyne. And if I try to break this apart here, I can't have an alkyne here. There would be too many carbons. So this part of it has to be the alkyne. So I have alkyne plus this. Really, there's not too many steps here. It's just the order. So from here, we can create a leaving group off of that one. So I'm going to start with the cyclohexane. Currently, there's no functional groups on here, so I need to add one. And I can use Br2 in light. And once I have my Br, that's going to be this with the leaving group. So I'm going to bring in the alkyne. This is NaNH2. And then if I add this to it, I get this. And then one more step, I need to get to the alkene, I need to do a reduction. So I can use H2 Lindlar. You could also use the sodium liquid ammonia because it is a terminal alkene. So I may have skipped a retrosynthesis step here. Right, so we go through the alkyne, kene to the alkyne, leaving group, and that is how it's broken apart. So this one was 3 steps as well. It was just the order of addition that is important here. Observations for number 1, halohydrin. We're adding carbons. This needs to get to an alkyne at some point if I'm going to add carbons. I know I can get to that with Br2 in water if I have this. And I know because I'm adding carbons along the way, I have to have an alkyne somewhere here. So it probably came from here. And in order to make an alkyne, I need 2 leaving groups, and that will take me back to here. So for my forward synthesis, I can use Br2 and a strong base in excess, followed by water will give me the alkyne, followed by water will give me the alkyne. At this point, I'm adding 2 carbons, so I need NaNH2. My 2 carbons. And I need to have a Z alkene here, so I need to use H2 Lindlar. And then I can add Br2 and water. And the OH goes to the position where the carbocation is the most stable. All right, number 6 is the last one, and this is going to be the trickiest one. Observations here is we have a ketone now. Before there was no functional group, so there's going to be a couple of things involved here. I know that I can make a ketone from an alkyne using water plus acid and the mercury sulfate. And that will give me the ketone. And if I'm working my way back here, I can make an alkyne from a dihalogen. I can get that from an alkene. I can get that from something with a leaving group, which I can get from there. Now this one is only a tricky one because of where the leaving group needs to be and where this most substituted position is. If it was just from here, it wouldn't be so bad, but because we have to go from having no functional group, that's what adds the extra steps here. So to go forward, I add Br2 plus heat, and that brings the Br to the most substituted position. I want to do an elimination here, so this is T-butoxide. And then brominate it at the least substituted, so I need HBr, ROOR. And that terminal alkene again, so T-butoxide. And now 2 BRs will give me, I'll use Br2 to get the dibromo, excess NaNH2, from here H2O, H2SO4, HgSO4 will give me the ketone. So that one is trickier. This one is 7 steps long. You wouldn't see anything this complicated on the final exam. But again, if you are able to get to this point, then you should be you are in good shape for the final.